Okay, the idea that you get in this section is that sometimes it's hard to solve an equation for y. Okay, it's very difficult, and sometimes it's impossible to just take some equation and get it solved for one variable. And you can still do the derivative, but you have to do it in a little bit different way. So just a couple of definitions. If something's solved for y, we call that the explicit form. That's what you've been seeing so far. You have usually y equals something, then you do the derivative, okay? But there's going to be times when it's very difficult to solve for y. So another example like this right here is the implicit form. Okay, that is not solved for y. That one's actually a very easy one to solve for y, but that's the implicit form. The explicit form would be like if you just divided both sides by x, then you would get y equals 1 over x. Okay, that's the explicit form. And then, of course, if you solve it for y, then you do the derivative like we've learned how to do. But if you can't solve it for y, then there's a different way you have to go about doing the derivative. A good example of that would be this function right here. Okay, try solving that for y and see how that goes for you. It's real difficult to get y isolated by itself on a side. Okay, so what we do in this case is we have to do what we call implicit differentiation, is what I'm going to introduce you to today. So the process, you have to follow a process a certain way. So the first thing that we're going to do is kind of get used to differentiating with respect to x. So I want to kind of go through this a little bit and kind of get you comfortable with this. And it's all about the Leibniz notation, understanding what it says. So this one right here, the variables match. So you're taking a derivative with respect to x. That's what you guys have been doing so far. So there's nothing to that. That's 3x to the second. We know we're done, right? Okay, but the key thing is this dx has to match the variable. If that was d dx of t to the third, it would be a totally different situation. And that's what you encounter when you're doing implicit differentiation. So here's what this says, and this is really a chain rule. So if you're doing the derivative of y to the third, you know how to do the derivative of y to the third. What is that? 3y to the second, right? But the thing is, when you're doing this differentiation, since they don't match, you actually have to do it this way. You have to, first of all, just apply the rule and get 3y to the second, but then you have to multiply by the derivative of that variable, like that. That's the chain rule. Really, you can think of this as y buried inside of, you have a function and a function, but y is the function. So you have to do chain rule. You do that, then multiply by the derivative of y. Now, the derivative of y with respect to x is not 1. Okay, those variables are different, so you just write it as dy over dx. That's what it is. So you just have to leave that notation. So anytime the variables don't match, you write it that way. So that's what the derivative is 3y squared times dy over dx. Okay, the reason we do this will make a little bit better sense once we start doing implicit differentiation. You'll see the point of that more. But for now, I want to just get you solid with what do you do when the variables disagree. If they agree, it's a piece of cake. That's what you already know how to do. But if they disagree, you've got that chain rule. Okay, so let's focus on this just for a few minutes and make sure we have this down. Okay, look at example A. Do the variables agree with each other? Yes. Okay, so we would say, yeah, the variables agree. So what we do is we just do like a power rule. Okay, and we're done with the problem. Okay, so what we would do is the derivative of this, we know the answer is 10x to the ninth. That's what we've been doing. Okay, piece of cake, right? Okay, look at the next one. What's the deal with the variables? Agree or disagree? They disagree. So you have to use a chain rule. Okay, so you have to do this just a slightly different. So you use the chain rule. And when you do this, you write your answer like this. Well, you go ahead and do the derivative of y to the 10th like you're used to. You say 10y to the 9th. But then you have to multiply by the derivative of y with respect to x. So see, when the variables disagree, you got to add that little piece in. Okay, that's a chain rule. You're doing the derivative of y with respect to x, and you don't know what it is. Okay, that's just notation. It's just written as dy over dx. Okay, does that make any sense? Okay, we'll get there. Okay, you'll start getting this once you get the hang of it. Okay, now what I'm going to do on this one is, we know that when we do a derivative of a sum, we can do the sum of the derivatives. So I'm going to go ahead and write it this way. This would be a problem you would do in your head, ultimately, but I want to go ahead and write this kind of key step on here. So it goes like this. Okay, first of all, look at this. Do the variables agree? Yes, so what's the derivative of 2x? 2. That's done. Okay, they agree when you did that, so that's what you do there. Now look at the next situation. Do the variables agree or disagree? They disagree. They're different. So what you do is you would do the derivative of that, which would be 8. I don't know why I'm putting a times there. That's a plus, okay, so we have plus. Then that would be 8y. But then what do? You do dy over dx. So when they don't agree, you always have that dy over dx in there. Okay, got to be that way. You can't mix up your variables. That's very important. The notation's real important. So that would be the way you would write the derivative, is like that.
So that's the reason why they leave that.
Yeah, okay. And when we do implicit differentiation, having that dy dx in your problem is going to be important, because that's what you're going to solve for. Okay, and we'll get to that in just a minute, and then you'll begin, I think, to see why I'm doing this more than you are now. Okay, let's do a couple more of these and kind of get the hang of this. Okay, this one, you have to use a product rule on, because the first function is x to the third. The second function is y. You have two functions that are multiplied, so this is a product rule. Okay, so when you do that, let's just carefully write it in the product rule formula. We have the first times the derivative, and the notation is real important on this. So times derivative of the first. Then we do it backwards. We say the second, and then we do times the derivative of the first like this. This would be a piece of a bigger problem that we're going to learn. So that's how that goes. Okay. Now, when we put this together, well, let's see. The x to the third is going to come down. The variables disagree on this, right? So what do you write? dy over dx. Okay, that's it. You don't see, really what happens is this. When you're doing the derivative of y, you know what you're really doing? You're doing the chain rule. You're saying derivative of 1y is y, but then you're multiplying by the derivative of y, which you don't know because it's a different variable. So you write the notation. That's why you do that. So we would just write this as dy over dx. Then we go to the next part. The y comes down. Okay, the variables agree there, so what is that answer? 3x squared. So there you go. That's how you write that. Okay, they only had that dy over dx when the variable didn't agree. Okay, does that make sense? Okay, all right. What kind of rule would you use on this next one? Quotient rule, right. Okay, so you got to get it set up in the quotient rule. So we're going to do the bottom, and we're going to multiply that by the derivative of the top. Write your notation very carefully. Minus the top, 3y, times the derivative. We're doing derivative with respect to x of sine x. And it's all over the bottom squared, so you can just write that as sine squared x, the way you learned in trig. So you want to get that set up like that. That's your quotient rule, bottom derivative of top minus top times derivative of bottom. So we only need to kind of figure out two things here. We need to figure that out, we need to figure that out, and then we're done. Okay? So I'm going to bring down the sine of x. Okay, variables disagree, so what's that? dy over dx, good. Okay? 3y, what's the derivative of sine x? Variables agree, so what's that? Cosine of x, good. So that's 3y cosine of x, and then that's all over sine squared x like that, and that's it. Okay? And what we're trying to do is prepare for the next thing I'm showing you. Okay? Yes?
Where did the 3 go when we did the derivative?
Which 3? Oh, I know what you're talking about. Where did the 3 go? Okay, I'm being sloppy here again. The 3 disappeared, so what's that going to be? What's the derivative of 3y? It actually should be 3 times dy over dx. Okay, my fault. So that will be 3 times dy over dx, like that. Okay? Yes?
Does the 3 stay with the dy dx? Or do you
Yeah, it's in front of it. So again, if you're doing the derivative of a function where the variables disagree, well, we know the derivative of 3y is just 3, right? But since the variables don't agree, that's why you put the dy over dx like that.
And would that be acceptable if we brought the 3 in front of the sign?
Yeah, that's acceptable, but it's probably preferred to write it as 3 sine x times dy over dx like this. So that's how you would handle the derivative of 3y. My fault for not putting that in there, okay? Okay, everybody following along what I'm doing? Okay, all right, now we'll kind of get to the y part here, and we'll kind of finish up here by starting to do some examples of implicit differentiation. These are just the prerequisite skills. So I've written on your notes what you do when you do implicit differentiation. As I'm going through examples, this is going to be what we're going to follow. Okay, so let's go ahead and let's do a couple of these to get started on here. All right, so the thing with this one is if you wanted to find the derivative of, and what you're trying to do is find the derivative of y with respect to x, you have two choices. One choice would be to solve it for y, then do the derivative. The other choice is to do it implicitly. And if you do it implicitly, you don't worry about solving for y. So here's how you start the problem. So start by writing this down. You want to do the derivative of the left side, and you also want to do the derivative of the right side. You have to do that to both sides of the equation. So that's how you always start off. The nice thing about implicit differentiation, you don't worry about algebra and solving for y. You're going to get what you want anyway. You're going to get the derivative perfectly. Okay, so let's do this kind of carefully now. So we're doing a sum. You can do this in your head if you want to. I'm just going to write that as the derivative of y squared plus the derivative of 3x and then the derivative of 8. Okay, just kind of piecing that together like that. That's a step you could bypass. Okay, so let's do this. So what is going to be the derivative of this part right here? 2y, then what? Times dy over dx. The variables do not agree. You know the derivative by power rule is 2y, but since they don't agree, you have to do dy over dx. That's the whole key to doing this. Okay, what's the derivative of 3x? 3. The variables agree, that's why we just stop at 3. Okay, so we're good there. And what's the derivative of 8? 0. That's a constant. Okay, so now what we're going to do is once you've done the derivative of both sides, the next thing you do is you solve this equation for dy over dx. You're trying to find what dy over dx is. So let me move this over here. So I'll have 2y dy over dx plus 3 equals 0. So now it's an equation that you're going to solve. You're going to isolate that dy over dx on the left side. So you can do this, just kind of move stuff. So subtract 3 from both sides. You would have 2y times dy over dx is equal to negative 3. And then how do you get rid of 2y? You divide by it. Okay, you got multiplication going on there. So you want to divide. So you're just solving an equation, but you're solving it for dy over dx. So what that means is the derivative is negative 3 over 2y. Okay, and that's how you would do that implicitly. That's your derivative. And it's okay that you have a y in there in your answer. That's fine, because you could solve this equation for y, but you would end up having a plus or minus square root if you did that. So it's a little bit better to just do it implicitly. That's it. Okay, you guys follow what I did? Okay, it's not that hard. Okay, they get a little bit more difficult as you get more stuff in there. So then the next thing we're going to do is we're going to find the slope of the tangent line at this point right here. Well, the nice thing about this is I've given you x and I've given you y. So if you're going to find the slope of the tangent line, well, what we know is that comes from the derivative, right? The derivative gives you a slope of a tangent line. So all you got to do on this then is you just do dy over dx, and you just evaluate that at whatever y is. So that's going to be sometimes I write this like this at, let's not do it that way. Let's just write the answer. Let's write it like this. So that's going to be negative 3 over 2. Okay, y is square root of 5. That's it. Okay, you don't plug in for x because the derivative is independent of x. So that means for your answer you would have negative 3 over 2 root 5. You probably can rationalize the denominator if you want to, but you don't necessarily have to. So I'm going to go ahead and do that. So then what I would have is negative 3 root 5. Then see, that would be 2 times 5. So that would be over 10 like that. Okay, so that's how you would find the slope of the tangent line, is just plug in to the derivative, and the 1 didn't make any difference. It turns out in this function, the derivative is only dependent on the y value. It doesn't depend on x. That's what makes the difference. Okay? All right, does that make sense? Okay? All right, so we'll run through a few more of these to kind of get us started on this. Next one's the same idea. It's a little harder. We're just going to find the derivative implicitly, then we'll find the slope of the tangent line. So let's do one more like that. Okay, this is an example of one that you would want to do implicitly. You could solve for y. It would be pretty difficult, so you don't even waste your time. So what I'm going to do is we're going to do the derivative of the left side. And we're going to do the derivative of the right side. And ultimately what we do is we solve for dy over dx. Okay, so you better have a dy over dx in your derivative or you aren't going to get anything. Okay, now when we do this, watch this real carefully. I'm just going to kind of do as much as I can in my head. Okay, what's the derivative of y squared with respect to x? What's that going to be? 2y times dy over dx. Good. Variables don't agree. That's why we do that. Okay. Now we got to do xy. How do you handle that? This is where students mess up all the time. Product rule. You have to do it, right? There's two functions. There is the first is x, second's y. You have to do the product rule. You must. Okay, so what we're going to do on this product rule is we go like this. We say the first times the derivative of the second, so we're doing the derivative of y. And we do it backwards. We say the second y, then we do the derivative of the first x, like that. So that's a product rule is what you've got going on right there. Okay. Then that leaves us with 3x. That's easy. What's that derivative? 3. The variables match, don't they? So x and x matches, so that's going to be a plus 3 like that. Then the right side derivative of 9 is 0, like that. Okay, so what I did on that is derivative of y squared is 2y dy dx. Doesn't match. Product rule here, variables match on the 3x, that's why it's a 3. Okay, is everybody okay? Okay, let's clean it up a little bit. We got a little bit more work to do before we solve for dy over dx. So that's 2y times dy over dx. This part right here is just going to be plus x times dy over dx. Okay, this part right here is going to be plus y. That derivative right there is going to be 1. The variables match, so that's just a 1. So I can do that, or just write it as y equals 0 like that. Okay, so that is doing the derivative. Now what you got to do is you have to solve for dy over dx. Okay, so you got to get the dy over dx by itself on a side like this. So here's how you do this. Anything that has a dy over dx, leave it on the left side of the equation. Don't even touch it. Just write it down and leave it alone. Okay, everything else is going to go to the other side of the equation. Okay, so if I do that, and it doesn't matter what order you put stuff, that would be a negative 3, and that would be a minus y. Just move stuff, change the signs, because you're really subtracting 3 and subtracting y, like that. Okay, now how do you get dy over dx by itself? You factor, right? You have to factor. Okay, that's a key. Okay, so you got to factor that out when you do that. So you're going to have dy over dx, and then that's going to leave you with 2y plus x is equal to negative 3 minus y like that. Okay, now what? Divide by what you're trying to get rid of. See, we factor that out, so that's multiplication. So now what you would do is divide both sides of this equation by 2y plus x. Okay, so that means your derivative on this is going to be this. And it doesn't matter what order you write all this in. You just dy over dx. You could factor a negative out of the top, but you don't have to. So we'd have that, and then we could have 2y plus x. That's fine. Okay, that's your derivative right there. Okay? Okay, that's the algebra. Okay, the algebra is not too bad on this level of a problem. So what we would do now is we'd find the slope of the tangent line. So what we're going to do now is you're going to plug into your derivative. Okay, so you have x is 2, y is 1. Here's your derivative. You have an x and y. You just simply plug in. So you're going to do negative 3 minus the y value, which is 1, all over 2 times y. Y is 1. And then plus x. And let's see, x is 2. So I'm just plugging in the point. Simplified, that'll give you the slope of the tangent line. So that looks like that is negative 4 over 4. So that's negative 1, like that. Okay? All right, does that look like something that you're following fairly well? Is there any questions about that? They get messier than these. These are kind of the elementary ones so far. They get messier. All right, let's see. Let's just do this this example, and then that'll end us up for today, I think. Let's see. So let's do one with the sine and the cosine in it. All right, trigonometric function. So, okay, we're going to do this implicitly. That one would be, you could solve that for y, but you would end up having something that's a little messy. So let's just do this implicitly. So we're going to do the derivative of the left side. Now what I'm going to go ahead and do is I'm going to write that as x to the 1/2, and I'm going to write that as 10y to the 1/2. And then the right side, I'm just going to do the derivative of sine x like that, because you know you're going to do a 1/2 power when you're doing the radicals anyway, okay? All right, so let's just kind of do each piece very carefully, all right? Okay, when we do this derivative, do the variables match? Yes, dx, x, right? They match. So just do a normal derivative. Do 5 times 1/2 x to the negative 1/2. You don't do the dy over dx because the variables match, okay? Now when you go to the next one, let's see, we're going to have 10 times 1/2 y to the negative 1/2. The variables don't match, so what do you have to have? Dy over dx. So you must put in that dy over dx like that. Okay, everybody with me on that? Okay, that's key. And what's the right side? Cosine of x. Derivative of sine's cosine. Okay, so we got that. Now, what you got to do is let's clean it up a little bit. Let's solve for dy over dx and see what we got going on here now. So I'm going to write this just as 5/2. And what I'm going to do actually on this, because we are going to find the slope of the tangent line, is I'm going to go ahead and just take that back to a square root, because we're going to have to evaluate it anyway. So bring the half down, change it back into a radical. Okay, over here, 10 over 2 is 5, so that's going to be minus 5. And again, I'm going to go ahead and bring that down to the bottom and do that like that. Okay, and then what I have is that's times dy over dx. And then that's equal to the cosine of x like that. All right. So what we need to do on this, and you'll get some kind of messy looking answers, is whatever has dy over dx, leave it alone. Don't move that. What you want to do is you want to take this whole thing and you want to move it to the other side. So what we would have with that is we would have negative 5 over radical y times dy over dx there. And that's going to be equal to the cosine of x, and then minus 5 over 2 radical x like that. So we have that. Okay, so what we want to do now you want to be flexible. Sometimes students have this tendency to just always want to divide by something. If you divide by that 5, you'll have kind of a messy looking problem. So I would suggest that instead you multiply by the reciprocal. Show some flexibility here when you do stuff. So I'm going to just multiply both sides by the reciprocal. It accomplishes the same thing. I did that so I don't have a complex fraction. I didn't want to have a fraction divided by a fraction. Okay, so what I would have then for my derivative is dy over dx. Okay, you can leave it in this factored form. You don't have to multiply this out. I'm just going to write this as, that first part I'm just going to write as negative root y over 5, and then cosine x minus 5 over 2 root x, like that. Okay, and that's good. That's a good derivative. That looks good to me. Okay, you can distribute out if you want to, but you're not required to. Okay, does anybody have a question about that? Okay, all right, now let's finish up just with the slope of the tangent line. Okay, so what we would have on this then is x is 4 pi, y is pi, so we're just going to plug stuff in and see what we get. Okay, we'll get a messy looking answer, but it ain't going to matter that much. So I'm just going to have negative y, so I put a pi there, and then I do over 5. Then I have x is 4 pi, so I do the cosine of 4 pi. Okay, and then I've got minus 5 over 2x. And let's see, x is 4 pi, so I do 2 times the square root of 4 pi, like that. Now there is a little bit of simplification we can do on that, so we want to do a little bit. Okay, this is a unit circle thing going on right there. What is 4 pi on a unit circle? What does that mean? 2 laps around the circle, right? 2 pi, 4 pi. So you end at 1, 0, so the cosine of 4 pi is 1. It's the x value, right? Okay, so what we're going to have now is we're going to have negative pi over 5 times 1. And then when you do this square root of 4 pi, well, you can take the square root out. You can do this in your head. But what you would have is, so you have minus 5 over 2. Square root of 4 is 2, but then you'd have a leftover pi, like that. Then the decision becomes, how much of this do I want to simplify? I'm not going to do much with this. I'm just going to do negative root pi over 5 times 1 minus 5 over 4 root pi, like that. And you could either leave it that way. I'm going to go ahead and do a distributive property and just multiply that out, because it looks like I got some stuff that'll cancel out a little bit. So if I do that, I'm going to have negative root pi over 5 for the first term. Negative times negative is positive. So I have 5 root pi over, and then 5 times 4 is 20. So you can write it like that. So I'm doing a distributive property. So what I'm going to have is negative root pi over 5. Pi's cross out. And then I've got 5 over 20 is 1/4. And that's probably good enough. You could also get a common denominator and put that over 20 if you wanted to, but you don't necessarily have to. Okay? So see, it gets a little messy with arithmetic, but that is the exact slope of the tangent line at that particular point on that graph. Okay? What makes that, what requires you to do that implicitly is you can't solve the equation for y. Okay? So that's what you're getting into in this section. We'll work on this a little bit more next time.